Time to start. So hello, everyone across the globe. We're happy to restart the Atto Fridays after a long break or a longish break. I hope you all had a great summer. And it's a pleasure for us to introduce Professor Takashi Tanaka. He is a group director in RIKEN, Spring 8 Center. He received his PhD from Kyoto University in 1997 and joined in Spring 8, a synchrotron radiation facility in Japan, for the development of undulators, one of the key elements in SR facilities. And he also conducted the development of undulators in SACLA, an X-ray free electron laser facility in Spring 8, and became a PI in 2013 to lead the Advanced X-ray Laser Group. Since then, his research focuses on the advancement of XFEL, including theoretical and experimental studies towards the generation of attosecond pulses in free electron lasers. And today, this is in fact the topic of his talk. He's going to talk about how to generate few cycle attosecond pulses in free electron lasers, and proposal and experimental demonstration. So we're going to hear how actually these things can be turned into reality, and we're looking forward to his talk. So feel free to start. The floor is yours, and welcome.
Okay, thank you for the nice introduction. I'm Takashi Tanaka from RIKEN Spring Center. Before starting, let me thank the organizer of this seminar series to give me this kind of opportunity to present our recent research results. Here is the title of my talk. It's throughout the few cycles second pulses in free electron lasers. So I'd like to make some proposals and show some experimental demonstration to realize this proposal. Here is the outline of my talk. Actually, I have prepared 3 topics after the introduction. The basic concept for to realize the few cycle FELs for the second pulses and its experimental demonstration. And then finally, I will mention the perspectives for the future, namely throughout the second free electron lasers. Let me first start with some introduction. I think that maybe many of you know already about what is a free electron laser. In the free electron laser system, we have the high energy electron beam, so it's actually composed of the free electrons. And then also we prepare the seed right, and then the seed right and the electron beam is injected to a device called an angulator, where the electron beam is wiggling along the sinusoidal orbit, as you can see here. So we have some periodic magnetic field generated by the device called the angulator. And then through the interaction between the seed right and the electron beam, the seed right is actually amplified by the electron beam to be shown here. So we have the amplified right and gets the raising, as in the other laser sources. And what is important is that we generate the what we call the micro bunching in the electron beam. This is actually the density modulation with a constant period, as you can see here. So we have the dense area and also sparse area, which is regularly arranged in the longitudinal direction. And then this kind of the micro bunching can emit a very intense coherent radiation and eventually amplify the light. So this is how the free electron lasers works. And as in the other laser sources, shortening the pulse length is a very important and also the persistent challenge in the development of the free electron lasers. Now, let me mention the theoretical limit of the FEL pulse length. And the pulse length in the FEL is very simple. It's very similar to that of the seed pulse length, as you can see here. So we have the pulse length shown here, which is very similar to that of the resultant FEL pulse length. as shown in this picture. So this means that if we reduce the pulse length of the seed right, we can eventually reduce the FEL pulse length, as you can see here in this picture. And if we continue this direction, one idea is to shorten the seed pulse length down to their theoretical lower limit, namely the monocycle duration. And then we have an impression that we can get the single cycle FEL as shown in this picture. However, unfortunately, this is not correct. And what we actually have is a several cycle pulse, as you can see here. And then in this case, we have the undulator periods of 4. And then as a result of the optical slippage, which will be explained in the next slide, the resultant FEL pulse length is also the 4 N cycles. In this case, we have the 4 undulator periods, and as a result, we have the 4 cycle pulse length. Let me now explain what is the slippage effect. This is a phenomenon that the light goes ahead of the electrons when the electron travels along the undulator, something like this. So during the motion along the undulator, the electrons is catch up with the light. For example, in this case, at the entrance of the undulator, the electron is located at the head of the light pulse. However, while it travels along the undulator, moving along the sinusoidal orbit, the light goes ahead of the electrons, and then it actually slips out of the electrons. And then at this point, the electron is located at some behind point in the tail side of the light pulse. So this is what we call the optical slippage effect. And because of this kind of slippage effect, even if we have the monocycle seed pulse, the resultant microbunching will be something like this. We have the many microbunches, even if we have the monocycle pulse. And even if we have the monocycle microbunching, even if we have the single cycle microbunching, the resultant FA pulse is also the merged cycle because of the optical slippage effect. So this means that we have some kind of the pulse stretch driven by the slippage. And so this kind of the slippage driven pulse stretch should be overcome or should be contracted in order to realize the few cycle free electron lasers. And then in 2015, we have found one solution to contract the slippage driven pulse stretch and to realize the few cycle FELs. Okay, then next I'd like to explain the basic concept to realize the few cycle free electron lasers. Here shows the layout of the seeded FEL, and in general, the undulator is actually divided into 2 sections. The first section is usually referred to as a modulator, and the second section is referred to as the radiator. And in between, we have the magnetic chicane in order to make a large detour of the electron beam. And then we prepare the seed light to be injected to the modulator synchronously with the electron beam. And then in the modulator, through the interaction between the seed pulse and the electron beam, the energy modulation is induced in the electron beam. And then after passing through this kind of the magnetic chicane or the very large diffraction trajectory, the energy modulation is converted to the density modulation to form this kind of the microbunches. And then once this kind of the microbunch is formed in the electron beam emits very intense coherent light, and eventually it generates the amplified radiation, or the FEL pulse is actually generated. And so this is actually the very, the conventional system of the seeded FEL. And in order to contract the slippage effect, what we have to do is very simple. We make very few modifications compared to the original conventional seeded FEL. First, we replace the seed pulse with a few cycle seed pulse, as you can see here. And second, we replace the modulators and the radiators with the tapered one. In this case, the magnetic field is buried along the longitudinal direction. in the both sides, tapered modulator and radiator, we have to make use of this kind of the tapered one. Taper means the magnetic field is actually changing gradually, as you can see in this picture. And then if we prepare the very short pulse or the few cycle seed pulse, the resultant energy chirp, energy density, energy modulation can be somewhat chopped. And then after passing through this kind of the magnetic chicane, we can expect that this kind of the chopped microbunch is induced in the electron beam, in which the microbunch is arranged with a changing, with a varying intervals you can see here. So in the frequency domain, it's chopped. And then once this kind of the chopped microbunch is generated, the electron beam can emit a few cycle FER path if it passes through this kind of the tapered radiator. So this is a basic concept to realize the few cycle FER path. And of course, we have the one necessarily condition that the interval at the nth microbunch, namely, for example, here is the first interval, the second interval, and the third interval, should be equal to the slippage length at the nth angular period. For example, here shows we have the first. Here shows the we have the slippage at the first period and the second period and the third period, something like that. So intervals at the nth microbunching should be equal to that at the slippage length at the nth period. So this is a necessary condition. And once this condition is satisfied, the chopped microbunch can emit the few cycle radiation as shown in this picture. Then now let me explain why the chopped microbunching can emit the single cycle radiation pulse. In order to do so, we focus on the current profile of the chopped microbunching and also the radiation waveform to be generated at each period of the undulator or the radiator. And here shows the current density profile in the time domain, in the temporal domain. So because the it is a chopped microbunching, the peak interval is changing along the longitudinal direction from lambda 1 to lambda 10. And then by means of this kind of the electron beam or the electron bunch, the radiation generated by this kind of the electron beam at each period of the undulator is something like this. So here shows the waveform of the radiation generated at each period, and this is actually similar to that of the current profile of the chopped microbunching. And then let us consider the radiation waveform generated after the first undulator period. And at each period, we have this kind of the radiation waveform to be generated. And at the same time, it should be shifted in the forward direction because of the optical slippage. In this case, we have the optical slippage length of the lambda 1. So the radiation waveform is shifted in the forward direction by the distance of the optical slippage lambda 1 compared to the original position. Then after the second undulator, and also we focus on this right pulse, namely what we call the resonant pulse. And then after the second undulator period, this kind of the waveform is further shifted in the forward direction by the second optical slippage at the second period, something like this. And then at the same time, in the second undulator period, we have another waveform to be generated, as shown here in the blue line. And as in the case of the radiation waveform generated at the first period, we have the optical slippage to be, and also it's shifted. The second waveform is shifted in the forward direction by the optical slippage of lambda 2. And then we do exactly the same thing at the third period and also the fourth period. Now it is obvious that the resonant pulse always undergoes the constructive interference. And for the other positions, the interference is rather destructive. Then after the 10th period, in this condition, all the radiation waveform is overlapped here. Then at the resonant pulse, all the waveform is interference of the radiation waveform is done in a constructive manner, as you can see in this picture. As a result, if we sum up all the waveform we can expect that the high power and the few cycle radiation pulse is generated by means of the trapped microbunching. So this is how the trapped microbunching can emit a single cycle radiation pulse. And we have made a lot of the research and the developments in order to realize the few cycle FERs based on this trapped microbunching concept in a theoretical study and also the experimental studies. And today I'd like to introduce the two topics. One is the experimental demonstration of the fundamental mechanism of the trapped microbunching, and the second one is the theoretical study. And we have recently made a proposal to generate the isolated attosecond pulse and also the twin attosecond pulse based on the trapped microbunching method. Okay, then the next topic is the experimental demonstration of the trapped microbunching method. Let me first explain the overview of this project. And here shows the bird's eye view of the Springate, the campus. So it's actually the large synchronous radiation facility operating in the western side of Japan. So we have the Springate storage ring. So it's an electron accelerator with a storage ring, named the synchronous radiation facility. And in the same site, we have the X-ray photon laser Sakura, shown here. So it's a linear accelerator to drive the X-ray photon laser. And in the same campus, we have a very compact storage ring, what we call the new Subaru storage ring, shown here. And this facility is very optimum for the demonstration experiments. In terms of the location, because I'm working in the Springate site, so the new Subaru is very near for me. And also the electron beam specifications shown here is very good for doing experiments, and also the layout is also very good. So this is the reason why we have chosen the synchronous radiation facility in Subaru for the demonstration experiments. And here shows the experimental layout which we have installed. The new storage ring or the electron accelerator is not actually the ring, but the storage, but the racetrack type, the accelerator. And we have actually the two long storage sections here and there. And we have installed the modulator and the radiator in order to do the experiments, demonstration experiments. And also we have installed the titanium sapphire laser for the short pulse seed laser. And also that we have installed the measurement system to measure the short pulse FER. This kind of the layout is very similar to what is known as a high gain harmonic generation FER, HGHG FER, except for 2 points. The first one is that we make use of the very short seed pulse. In our condition, we have compressed the seed pulse down to the less than 5 cycles. And also the modulator and the radiator is a tapered undulator. So we have actually 2 points. And except for the 2 points, this layout is exactly the same as the high gain harmonic generation FER. And here shows the progress of the project. The first proposal of the trapped microbunching scheme has been made in 2015, so it's about 8 years ago. Then 3 years later, we have started the project for the experimental demonstration. And after that, we have made a preparation for the accelerator and developed the components such as the seed laser and the timing system, and the tapered undulator and the measurement system. And then after 4 years, we get the first raising in 2022 in the February. And then 1 year later, we have successfully demonstrated the basic concept of the trapped microbunching scheme. So I'd like to report the experimental results of this project. However, before that, let me mention something about the technical development, because we have made a lot of the developments to realize the experimental demonstration. And the first one is a tapered undulator. Here shows a picture of the very special undulator which we have constructed. In this undulator, each parallel is equipped with the gap motion, namely the gap of the undulator, namely the top and the bottom magnetic distance can be independently tuned for each period. So this means that we can arbitrarily apply the field gradient in the magnetic field of this undulator, and at the same time we can change the effective number of the undulator periods. The constructed undulator has a full period of the 24 periods is actually available. However, by effectively detune several periods, we can reduce the number of the undulator periods. So this is the constructed tapered undulator. And second is the tighter the seed pulse laser. So this is also a very important component. We have installed the mode-locked titanium sapphire laser with a wavelength of the 800 nanometer and also the rep rate of the 1 kilohertz. And also we have chosen the hollow fiber compression scheme in order to shorten the pulse length of the seed pulse. And we have also here shows the several components. Sorry, there are many Japanese characters, but anyway, so we have implemented this kind of the hollow fiber compression scheme. By means of this technique, we have compressed the seed laser pulse from the 50 femtosecond down to 12 femtoseconds. So it's about a factor of 4. So we can choose, we can make use of the long seed pulse or the short seed pulse. Third component is the timing system between the electron beam and also the radiation pulse. I skip all the details. However, we have achieved the timing jitter of the less than 10 picoseconds. I should say that this timing jitter is not very good compared to that that is achieved in the FEL facility. However, this is sufficiently good compared to the electron bunch length in the storage ring. It's about the less than 100 picoseconds. So compared to this kind of the long electron bunch, this kind of timing jitter is sufficiently good. And after this kind of the technical development, we have succeeded in the generation of the coherent radiation in 2022 February. So here shows the time resolved spectrum of radiation, which has been measured by the slit camera. And you can see several background here. So this comes from the spontaneous radiation as a background. However, we can see this very bright spot around here. So this is the actual coming from the coherent radiation. So this results show that we have succeeded in the coherent radiation generation in this by means of the many components which has been installed in this project. And here shows a picture of the several guys. I'm here, and the other guy is actually smiling at this point. And then we have now finished all the commissioning for the experimental demonstration. And then now let me show you the several results of the experiments. Let me first explain the how to demonstrate the fundamental concept of the chopped microbunching. And here shows the experimental layout, essence of the experimental layout. We injected the seed pulse with a wavelength of the 800 nanometer to the modulator synchronously with electron beam. And then we generate the coherent radiation at the second harmonic, namely the 400 nanometer. Of course, we can generate the 800 nanometer coherent radiation. However, it's very difficult to separate from the 800 nanometer wavelength seed pulse because the seed pulse is very, very intense. So it's very difficult to separate the seed pulse and measure the coherent radiation with the same wavelength. So we have given up to generate the same wavelength radiation. And then we decided to generate the second harmonic radiation by tuning the radiator setting. And by means of this change, we can separate the seed pulse from the coherent radiation because we have the very large change in the wavelength of radiation. And at the same time, this is a very, eventually, this was very good for us because we can demonstrate the chopped microbunching scheme, not only in the fundamental radiation, but also the high harmonic radiation. And of course, in order to go to the shorter wavelengths and also the shorter pulse lengths, we have to apply this scheme to the higher harmonics. So this is very important to demonstrate the high harmonics. So this is the reason why we have chosen the second harmonic. And also we have measured the spectrum of the coherent radiation with various conditions. For example, we can choose the seed pulse length, the long seed pulse or the short seed pulse, and also we can change the Angela periods. The 4 periods is the 24, and also we can halve the period, and or we can make use of the quota period. 24 and 12 and 6 period is also available. And also we can apply the taper gradient without any taper, or we can apply the taper. So this is actually the eventually optimized taper 11%. And using this kind of the various condition, we have repeated the main spectral measurement, which will be explained in the next slides. Here shows the spectrum of radiation in the basic condition, namely the pulse length of the 48 femtoseconds, and we have the 24 Angela periods. So this is a 4 periods, and also we apply no Angela taper. And in this case, the bandwidth is around the 6 nanometer. And if this is fully limited, the pulse length of coherent radiation or the FER pulse length is actually the 40 femtosecond. And this is actually a very reasonable number, because we have injected the seed pulse with the pulse length of the 48 femtosecond. And as a result, we can get the pulse length of about the 40 femtoseconds. So this is very similar. So actually, this is a very reasonable result. And what we have to do is to broaden the spectrum of the coherent radiation or the FER pulse length in order to shorten the pulse length. And one idea to do so is to apply the Angela taper. And actually, the Angela tapering is usually done in the synchrotron radiation facility. So we have tried to apply the Angela taper by the taper gradient of the 11%. And the result is shown here. And the result was actually very disappointing. I mean, that there is no broadband, there is no broadening in the broadband, broadening the bandwidth, as you can see here. And at the same time, we see the intensity is significantly reduced from this end to that one. And actually, this comes from the fact that the spectrum of the coherent radiation is dominated by the that of the seed pulse. So even if we apply the Angela taper, the bandwidth cannot be broadband because the spectrum of the coherent radiation is dominated by the seed pulse. So this means that we can apply we can compress the seed pulse in order to broaden the coherent radiation. And actually, we have tried the seed pulse with the pulse length of the 12 femtosecond by the hollow fiber compression scheme. However, as you can see, in the coherent radiation, the bandwidth of the coherent radiation is still 7 nanometers, so it's not very much different from the original one. And in this case, the pulse length is about 34 femtosecond. So this means that because we have injected the seed pulse of the 12 femtosecond, however, the resultant coherent radiation pulse length is about 34 femtosecond. So it's about 3 times longer than the original pulse length. This is apparently coming from the pulse stretch by the slippage effect. So I think this is our first time to see this kind of the pulse stretch by the slippage effect, I think. And then, so because we have verified the pulse stretch by the slippage effect, we can reduce the Angela period in order to relax the slippage effect. And actually, we have tried 2 Angela periods, 12 periods, and 6 periods. And as expected, we can broaden the spectrum of the coherent radiation. So the green one means the 12 periods, and the cyan one means the 6 Angela period. and we can actually significantly broaden the spectrum of the coherent radiation. However, at the same time, the intensity is reduced significantly, as you can see here. So please note that we have I applied some scaling 20 times and also the 200 times. So this means that we can get a very broadband radiation. However, intensity has been reduced very much. So reducing the undulate period is not a realistic way of the generating the single cycle FA radiation. So then we finally tried the undulate tapering to examine the chopped microbundling scheme. So we apply the short seed pulse and also the undulate taper with a taper gradient of the 11% in this case. And as you can see, especially compared with the fewer undulate pairs, we can get a broadband spectrum, and also at the same time that we can get a much higher intensity compared to the fewer undulate pairs, as you can see here. Of course, compared to the original intensity, it is somewhat reduced. However, we can get there still intensity, still intense, and also the broadband spectrum of radiation is actually obtained by applying the undulate taper. And if we define the bandwidth from here to there, of course, it's somewhat very difficult to define the bandwidth because of this kind of the somewhat very specific specular, how say, radiation profile. It's very difficult to define the broad bandwidth. However, if we define the bandwidth to be 28 nanometer from here to there, the resultant pulse length is about 9 femtosecond. So this means that by applying the undulate taper, the pulse length is reduced down to 9 femtosecond from original 34 femtosecond. So we can compress the pulse length from 34 femtosecond to 9 femtosecond. So it's about a factor of 4. So this means that we can succeed in the pulse length control by the undulate tapering and also the short seed pulse. So this means that we have successfully demonstrated the chopped microbundling scheme. In practice, we have made a comparison with the theoretical prediction, namely the numerical result. So the comparison between the two shows a very good agreement between the experimental and the numerical results. So we have concluded that we have succeeded in the experimental demonstration of chopped microbundling. And we have recently published in a paper. So it's about 1 month before in a physical review letters. And it is published in the PRL in the editor's suggestion. So now we have succeeded in the experimental demonstration. I'd like to move on to the next final topic, namely the perspectives toward the second free electron lasers. And actually, we have made a lot of the proposals to realize the second FEL, based on the chopped microbundling scheme. And in the early proposals made in the 2015 and the 2016, we have had a very stringent requirement of the electron beam, or we have suffered from the strong satellite pulses. So we have continued the theoretical studies in order to overcome these kind of difficulties, and we have finally succeeded in the proposal of the the concept to realize the isolated few cycle FEL pulses. So this is based on the introduction of the special radiator to do the function separation, which will be explained later. And based on this kind of the concept, we have theoretically demonstrated the generation of the isolated monocycle pulse in this paper. In this paper, we have proposed an idea to eliminate the satellite pulses and to generate the isolated monocycle pulse. And also we have published a paper to make a proposal to generate the tunable double pulse. And this is very important to do the pump and probe experiments. Okay, so this kind actually these two schemes are very similar, and I will explain the basic layout first. And it's very difficult. It's very similar to that of the original layout. However, you have some modifications. And first, we have changed the monocycle seed pulse to the chopped seed pulse. But at the same time, we have to reduce the number of modulator periods. So in this case, we have just 2 periods. However, even with this kind of the combination, we can generate the chopped microbunching, as you can see here. And then we inject this kind of the chopped microbunching to a very special radiator whose component is shown here. It's actually composed of the 2 sections, subradiator and also the retarder, which will be explained later in the next slide. But anyway, so if we make use of this kind of special radiator and also the chopped microbunching, we can generate the isolated monocycle pulse, which has been theoretically demonstrated. And now let me explain the magnetic field distribution of the special radiator. So the magnetic field distribution of the magnetic field is plotted as a function of the longitudinal coordinate. And it's actually composed of the special, the subradiator and also the retarder. So here shows the magnetic field profile of the subradiator. It's very similar to each other. And also here show the magnetic field profile of the retarders. So retarder plus and retarder minus means that the polarity is completely flipped from this end to that one. As a result, the radiation pulse generated in the retarder is actually cancelled out in the next retarder because of the polarity flip, because of the flipped polarity. As a result, the retarder just works to control the slippage length in each period of the radiator. And then we can generate the monocycle or the isolated pulse from these subradiators and also the next subradiator. So this is how this special radiator works. Okay, then let me show you the parameters which has been done for the numerical simulation to theoretically demonstrate the scheme. I skipped all the details about this end, and let me show you only the result of the simulation. However, before that, let me show you the temporal profile of the current profile of the chopped microbunching using this kind of the parameters. This shows the current and also the plotted as function of the time. So this shows the temporal domain of the chopped microbunching. And in practice, in the tail side of this chopped microbunching, the interval between the microbunches is about 1 femtosecond. And on the other hand, in the head part, the interval between the microbunches is about the 0.7 femtosecond. So the interval is actually changing from tail to head. So this is actually the chopped microbunching is actually generated. Okay, then if we inject this kind of the chopped microbunching to a designated special radiator, we can expect that this kind of the isolated monocycle pulse in the attosecond region is actually generated. Is the radiation power reaching the gigawatt level in this example? And if we zoom in this area, we can see that the monocycle radiation is actually generated in this example with a pulse length of the 45 attosecond. And then the advantage of this concept is that the waveform of the attosecond pulse can be actually flexibly controlled. This comes from the 2 different functions in the special radiator. Namely, the subradiator can generate a pulse, right pulse actually. However, in the retarder, the radiation pulse generated in the retarder is actually cancelled out, and it actually works just to control the slippage. As a result, the specification of the subradiator dominate the right pulse properties. For example, if we control the magnetic field of the subradiator, we can adjust or tune the pulse length of the isolated monocycle pulse. And if we tune the phase of the magnetic field of the subradiator, we can control the carrier envelope phase of the right pulse. And also, if we can change the number of the angular pairs in the subradiator, we can also tune the number of the cycles of the right pulse. Here shows one example to tune the pulse length of the single cycle pulse. So this is a result of the simulation for different magnetic field strengths of the subradiator from 0.7 Tesla to 1.5 Tesla. And by applying the stronger magnetic field, the radiation pulse length is actually expanded from black to red, green, blue, and CM. So we can control the radiation pulse length by means of the tuning the magnetic field of the subradiator. And second example is to tune the carrier envelope phase and also the number of the cycles. So this is actually possible by changing the number of the pairs of the subradiator from one period, 1.5 period, 2 period, and then 1.5 periods. So the blue one shows the single cycle duration, and the green one shows the 2.5 cycle duration. So we can change the number of cycles, and at the same time also we can tune the carrier envelope phase, which is obvious from this kind of example. The final result is to generate the double pulse, and this is actually possible by two schemes. I just showed you one example. This can be done by adjusting the slippage condition by means of the retarder in the radiator, and then we can generate the two pulses from the same chap microbunging. I just show you the result of the numerical simulation. So you can see there two right pulses are actually generated in each example, and actually the delay between the two pulses is actually controlled from 0.2 femsecond. So this is 200 second to some tens of the femsecond. So by changing this kind of the temporal delay, maybe we can do the palm probe experiments, I think. Okay, so this is the final slide, and now let me summarize the talk. I have presented the chopped microbunging scheme to realize a few cycles at second FEL. And as I have presented, significant advancement has been made in the theoretical and also the experimental studies. And I hope that this kind of the new light source can open the way to the application, to the new application of the attosecond pulses. Okay, now let me thank you for attention. But before that, let me thank all the collaborators for the experimental studies and the theoretical studies. Okay, thank you for attention.
Thank you very much for this really nice talk. Other questions, comments? Please either raise your hands or type your question in the Q&A. We are all ears. And I understand sometimes people are quiet, but let us start. Yeah, people are quiet today. Ah, there is one. Okay. It was a very informative section, but sir, what would be the effect of this new attosecond physics on your life? This is from Shahab Tariq. So do you mean applications, or do you mean, I think he means what would be the main applications of having this X-ray attosecond pulses from XFEL?
Yeah, but I think it's very difficult to answer for me because I'm just physicist of the accelerator side or the light source development. So it's very difficult for me to give the right answer. However, I hope that the new development of the new light source always led to the development of the new science, I hope. So this is my answer. So it's very difficult. Sorry, but it's very difficult to give you a good answer. I'm sorry.
Okay, he's asking if it would be possible maybe in the future to speed up the processors. Like
Yeah, I think so. Yeah, of course, exactly.
Okay. Thank you. I mean, I understand that you're trying to achieve higher intensities, right, for these pulses that you're trying to generate. So this would be making a big difference, right?
Yeah. Right.
Okay. Any more questions? Hello? We see a lot of people here. Feel free to raise your hands. We have one more. Thank you so much. Shahab, Tariq, enjoyed very much your talk. And he's thanking you. If you are shy and don't want your questions on YouTube, one possibility is to wait until we go off records, and then you have the opportunity to ask questions as well. But I mean, it is a good opportunity, and I mean, they're building enormous things in Japan, and it is a really important milestone in this technology. So I would definitely encourage our audience to ask a few questions and also say hello to the speaker. I mean, one question of someone who doesn't understand a lot about instrumentation and let me see who. Hori Siampur, thank you for the interesting talk. What is the energy efficiency of chirped method for making these very short pulses?
Energy efficiency, I mean, maybe I think this is similar to what is actually achieved in the FER. So maybe it's very difficult to say, but maybe 10 to minus. No, sorry. Maybe 10 to minus 4 or something like that, I guess. It's very difficult to say the exact number. But in the simulation, I think it's no. Maybe 10 to minus 3 or 10 to minus 4 or something like that, I guess. It's very difficult to say exactly the number without doing some kind of simulation, I think.
Okay. Would you like to also speak? Because we have quite a few questions as well. But
there are big questions in the Q&A, I think. Can you write?
Yes, there are quite a few ones. So that's why I'm saying, because Hori raised his hands.
Okay.
So we'll see. Okay, so go ahead. But we have quite a few in Q&A as well, so I'm pleased.
Do you hear me?
Yes, we can hear you loud and clear.
Thank you for the talk and for your answer. I mean, I see that the efficiency, the energy efficiency is very small. I am not an instrumentalist, but I wanted to know, is there any possibility to improve this efficiency, for instance, because the picture that you showed for the waveform of the, I saw that there is a lot of in fact, the annulating interference between waves. Therefore, is it possible to somehow shorten this the part that they annulate each other and just in some way making the pulse, that the small pulse that is desired more efficient?
Okay. I think that there may be several, how to say, combination of the parameters to enhance the output pulse. And what I have shown is just one example to demonstrate to theoretically demonstrate that the gigawatt level attosecond pulse is available with this scheme. However, of course, there are many infinite number of the parameters combinations. I think so. Maybe we can look for the good and real, realistic parameters to be actually implemented in the real machine. So I think there are many way of the improvement of the the output, I think. But right now it's very difficult to say exactly what is actually the efficiency. So this is my answer right now. But there are the number that I have shown in the simulation is not the unique solution, I think.
So,
Thank you very much.
Thank you very much. The next question is from Wilhelm Becker from the MBI. Hi, Wilhelm. He's asking, can you elaborate on the analogy with attosecond pulses produced in atoms? This is the effect of the bandwidth. Can you run your attoseconds on the FEL harmonics?
Yeah, that's possible, I think. Just a moment, but can you count? Yeah, actually, I'll say in any case, we have to go to the higher harmonics in order to go to shorter wavelengths. And in the numerical example that I have shown in the final slides, it's I don't remember the exact number, but maybe 10th harmonic or something like that. So in that case, in any case, we have to go to the high harmonic. I'm not sure if it's analogy with the I'm not sure if it's really the analogy with the attosecond pulses in the atom. But anyway, so we have to go to the higher harmonics.
Yeah, Wilhelm, feel free to ask questions if you wish. You are
can you hear me?
Yes, we can.
Okay. No, I wondered because, for the attoseconds in atoms, the bandwidth is absolutely crucial. No bandwidth, no attosecond pulses. And now I wondered because in your talk, you never mentioned the term bandwidth.
Okay. Okay, I see. Bandwidth is actually the Fourier limited. Now, how to say? It's in any case, the attosecond pulses generated in this scheme is of course Fourier limited. So it's very similar to that generated in the other method.
Okay, thanks.
Yeah.
So is that clear? It's actually an interesting point because it is paramount. I agree. We have also from Andrei Benediktovich, could such an approach be generalized to the X-ray domain? And what are the main limitations for going to shorter wavelengths?
Yeah. Okay. Yeah, actually, this is a very good question, I think. And the one idea is to apply this scheme twice or 3 times. I mean, they're cascading the scheme. So even if we start with a very long wavelength, for example, 200 something like 200 nanometers, something like that, we can go to the, for example, the 10 nanometer or something like that. Then by using the 10 nanometer, 10 nanometer wavelength radiation as a seed of this scheme, we can go to the, for example, 1 nanometer or something like that. So we can repeat this kind of the cascading the scheme, then we can maybe reach the X-ray region. Theoretically, I think.
Okay, is this fine? You can also speak if you wish. I have unmuted you.
Yeah, thank you very much for the reply. So can you foresee at some point to apply this scheme at SACLA? We need to have 10 keV radiation.
Excuse me, I do not hear you well. So your question is, are we going to implement this scheme in SACLA? Is that right?
Yeah. So is it potentially possible?
Of course, my final goal is, of course, to implement the scheme in SACLA. However, we have to many things to do before that. And the experimental demonstration has been done just in the visible region. So in any case, we have to go to at least the UV region or something like that. So before actually implementing in the SACLA, XLFA facility, we have many things to do, I think. This is my answer.
Thank you. Very promising. Thanks.
Yeah, welcome.
Are there further questions? Okay, if not, let's thank the speaker again.
Thank you very much.
Thank you.
Yeah.
And I wish you all the best.